So good afternoon, everyone. Welcome to the second lecture in our March mini-school on parallel computing with GPUs by Martin Bucher and Japie Greeff. My name is Francesco Petruccione. I'm the interim director of NITheCS, and I'm sorry that I missed the first installment, but I was away in a different time zone and it was not so practical. Yeah. So today, I think Professor Greeff will give the second lecture, and Professor Bucher will answer all your queries in the chat and the Q&A. Yeah. So Japie, your first slide is already up and running. You're most and welcome to start the talk. Yeah. And the participants online, you know the game of the chat and the Q&A. So, and at the end of the talk, if time permits, we can even allow you to ask your questions in person. Yeah. So Japie, please, thank you very much for the lecture. Yeah.
Thank you very much, Francesco, and welcome everyone to this second session on introducing programming with CUDA, obviously specifically in C++. I think all of you will have probably attended the first lesson, so I'm not going to read the little introduction to this. I will again, however, highlight we are, Professor Martin Bucher and Professor Japie Greeff. We're the same team as last time. It's just that this time I will be presenting the lecture and Prof. Martin will be answering your questions in the Q&A. So as they come up, please send the questions as soon as possible so that he can answer them as quickly as possible and we don't necessarily have a huge bulk in the end. Okay, so for this lesson, we're going to look a little bit more at architecture and specifically the differences between CPUs and GPUs. We're then going to look at the programming model for using CUDA GPUs in a little bit more detail. We're going to go through a program for vector addition, as well as getting some device characteristics in quite a bit more detail than what we did last time. And then I just want to send you or show you some links on installing the system for yourself so you can play around on your own hardware. We are working on the machine that we want to get you the user accounts for. There is just a problem with the driver in the latest version of Ubuntu because the card we have is slightly newer than what is in the repository. So the examples I'm going to show here today were actually done on a Windows machine. So I will show you how to go through the Windows installation. And then as soon as we have the user accounts available for Linux, we will obviously share those in the next lesson, hopefully. Okay, so in terms of architecture, obviously all of these chips, whether they be CPUs or GPUs, are based on this concept of transistors. Okay, so this is the base component that is used for basically all logic. And the size of the die that each of these chips is built onto is determined by the number of transistors that are on it. Okay, but the physical allocation of the resources in the form of transistors and the number of transistors is fundamentally different between CPUs and GPUs. So if we look at two chips that have the same number of transistors on them, we will look at the allocation of those transistors to different functions inside of the two different chips to give us an idea of how they differ and how they will operate in different ways. So, I mean, the basic concept that we will look at first is the CPU. There we looked a little bit at what CPUs are in the previous lesson. But really, when we're looking at CPUs for fast processing, what a CPU is going to try and do is decrease the latency in getting access to information from its caches, from the memory as a whole. And it's going to do its processing really, really fast in a very small number of threads. Okay, so in order to decrease this latency, it's going to do lots of clever things with logic. So it's going to do things like pipelining instructions so that they can run one instruction per clock cycle. We're going to parallelize instructions on the same core, even different cores. So there's a lot of tricks we can pull in the control logic of each of the cores on our CPU. But as we saw in the last lesson, the speed at which the clocks can run has kind of stagnated. So we really can't run the transistors faster than what we are currently running them with the current technology. So what we will see over time is that although you can, cluster CPUs, so there are options like Beowulf clusters and things like that, where you can have, a very large number of CPUs running in parallel. That is quite expensive because obviously a CPU core is quite a bit more complex. And what we will find with our GPUs is there's less control logic, but a huge amount of cores that are allocated on a GPU compared to what we will see on a CPU. So let us first consider the CPU in a little bit more detail on what it is comprised of. Okay, so we'll take this generic view of a CPU, and we will look first at the sort of basic building block there, which is the core. Okay, so inside of the core of a CPU, obviously most CPUs you buy these days, unless they are embedded systems, have multiple cores per CPU. But each core in this processor is going to be comprised of an arithmetic logic unit, which is going to perform, the logic and arithmetic calculations on the registers that are inside of the core. And it's also going to have a clock unit, which is going to select, from the instruction register, what instructions the arithmetic logic unit needs to run. And it's all going to be timed by a common clock. So the cores between, in most instances, the cores on the CPU are going to share a clock. There are instances where you will have different clocks and different kinds of cores, but for the most part, that's not going to be the case. What we will also find is that on the core, there will be L1 cache, which is specific to that core. So in this diagram, we've got 4 cores. So those are the green, purple, and yellow blocks on the top left. So that's the sort of rough architecture of just the individual core inside of the CPU. But now if we look a little bit wider at the concept of cache, and specifically cache as it refers to memory, okay? There are 3 levels of cache that you will use inside of a CPU, okay? The fastest one is going to be the L1 cache, and this is split between a data cache and an instruction cache. And this is specific to each core. So each core has its own L1 cache. L2 cache is also specific to each core, but it is a little bit slower than the L1 cache, but it is also bigger. Okay? L3 cache, or level 3 cache, is the largest cache that is available, but it is also the slowest cache, and it is shared between the different cores. So what I've done here, I've put a link on the top right in the slides, which we'll obviously make available again, to a program called CPU-Z, which is just a tool that allows you to characterize your system. So this is obviously looking at my specific system and the CPU that I have on this laptop. And what we will see is that I've got an Intel Core i7, and inside of this Intel Core i7, there are 3 levels of cache. In some processors, there are 4 levels of cache, but that is quite rare. But in this one, I've got 3 levels of cache. My L1 cache is split between data and instructions. There's obviously 4 of them because there are 4 cores, and each of those caches is 32 kilobytes in size. The level 2 cache has obviously again got 4 versions of it because there's 4 cores, but it is much larger at 256 kilobytes. And then the level 3 cache is 8 megabytes in total, so much larger, but this time not 4 times that. It is shared between all 4 cores. Now, from a technology perspective, generally your level 1, 2, and 3 cache is going to be made up of SRAM or static RAM, which is much faster than DRAM or dynamic RAM. But this is obviously where the trade-off comes in, because static RAM is physically much larger on the processor. So it takes up a lot more space that you obviously trade off for the speed. Whereas DRAM, although it is much slower, is a lot more physically dense. So it is optimized for capacity rather than speed. And the way processors are designed, these caches are matched. And they're designed in very intelligent ways, but they're matched in such a way that memory bandwidth can remain fairly constant. So what we mean by memory bandwidth is your ability to fetch instructions and data from the memory of the machine in a constant amount of time. So whether it is access from the level 1, level 2, or level 3 cache, or hitting the memory more directly, we want to make sure that those instructions happen fairly consistently in terms of time. But obviously there are things like cache misses where you will obviously have to go fetch the information from the main memory, which then just slows down your process. Now, in addition to the size of these caches, they are also split up into a number of ways, okay? So a way is basically how the cache is associated to main memory. So this indicates how many locations inside of the main memory, each location in the main memory can be mapped to a specific cache. So if you have, for example, one-way cache, which I show in the top left image there, the main memory, each individual memory location can only live in one specific memory location in the cache. So for example, there, index 0 and index 4 can only live at index 0 of the cache memory. So that would be a one-way cache. A two-way associative cache means that each index inside of main memory can live in two places in the cache. So there's a little bit more flexibility there. Obviously, that means more lines need to be drawn inside of the processor. So there's a trade-off here between the number of ways that are available, which obviously decreases the chances of cache misses, but obviously increases the complexity of the cache, making it not able to keep as much SRAM on the die. Okay, so what we will see is in my processor, the level 1 cache is 8-way. So each position in the main memory can be allocated to 8 positions inside of cache memory. The level 2 cache is only 4-way. And level 3 cache is 16-way. So there's much more flexibility on the level 3 cache, but again, it is slightly slower, whereas the level 1 cache has some flexibility, but is very, very fast. And level 2 gives us basically the middle ground between those two things. Now, we mentioned earlier that each core can also handle a number of threads, okay? So it's no longer the case that each core only has one thread, but in this specific instance, each of the cores inside of my i7 can handle 2 threads, which means that for the hardware of this specific CPU, we can have 8 threads running at the same time while we are running in our programs. Okay. So that is the general design of our CPU, specifically as it relates to memory. So now let's switch over to the GPU. And what we will see here is that there is a huge difference in the way things have been mapped out. So what I've done here is in this image, we've got the cores marked in green. So you'll see how much space they take up. And then the cache marked in purple and the control logic marked in yellow. The same colors are going to move over to the next diagram. But here you will see a huge amount of the die is allocated to the cores where the actual processing of data is going to happen. Okay, there is a little bit of space allocated to the control logic and the level 1 cache that is available to each of the streaming multiprocessors. And then there is a similar sized level 2 cache and then access to the same kinds of DRAM as what we'll have on the CPU. Okay. But when we talk about memory inside of the GPU, what we're going to find is that we actually need to consider 2 different things. The one being the physical memory and how things are physically laid out on the die. And then at the same time, we need to consider the logical programming model, because how we access the physical memory is not necessarily going to map one-to-one in the way that you think it should in terms of the physical layout of the chip. And fortunately, our libraries are going to help us to do that in an optimal way. But if we do consider the physical layout of the GPU, it is split up into a number of streaming multiprocessors. And each of the streaming multiprocessors has its own control logic, its own registers, a constant cache, a level 1 cache, and then a shared memory for all of the cores that are inside of that streaming multiprocessor. As I mentioned, there is a level 2 cache, but the level 2 cache is shared between the different streaming multiprocessors, whereas the level 1 cache is specific to each streaming multiprocessor. Now, we're not going to touch on the constant cache or the texture cache in this course, but basically those will be used more when you're doing graphics work, specifically the texture cache. So there's dedicated cache for graphical operations, because obviously these GPUs have generally been designed for operations in a graphical space. But we do have access to the texture cache as well as the constant cache. But what we're going to be using predominantly is our level 1 cache and the registers. Now, obviously, the streaming multiprocessors or the cores inside of them can access things in the level 2 cache, but they can also access things in global memory. But you need to pay attention to where in memory you're pulling things from, because synchronization and the time it takes to get information from these memories is something that is not quite as hidden from you as what it is when you're programming on a CPU, which takes care of a lot of that heavy lifting for you while you're programming. So now, if we switch over from the physical layout to the logical layout, what we are going to see when we are coding is that we're going to be thinking with the concept of blocks and threads. Okay, so as we send information to and run functions on our GPU, we're going to indicate to the GPU how many threads we want to run inside of blocks that we're going to split up into grids. Okay, each of the threads inside of our logical layout is going to have access to its own little local memory. So that is memory that is specific only to that one thread. But it can also access all of the registers inside of the block, as well as the shared memory, which is inside of the block, okay? But then the global memory, constant memory, and texture memory is going to be shared between blocks. But again, we sacrifice speed for having access to this larger memory, okay? And then we are obviously going to run certain things in parallel on our GPU, but we're going to interface this predominantly with our CPU, because our GPU is really not built to run, sequential programs that are of any kind of size. What we want to do is run very short pieces of code that are run in parallel very, very quickly and have, the long sequences of code run by our CPU for us. But we will see now how we make this distinction. So basically, the two devices, or the two things that we speak about when we are looking at where we want to run our code, is going to be the host. So that is what we refer to, or the CPU that we refer to in our system. And that is going to run basically, well, I say serially, it's actually sequentially. You obviously have the ability to run things in multiple threads and asynchronously, but for the most part, when we're thinking about programming CPUs, things are going to be running quite sequentially. And from this sequential code, we are going to be calling kernels which run on our device, which is what we refer to our GPU as. And each of those kernels are going to run inside of a grid. Okay, so a grid is just a number of blocks, as we will see in a moment. Okay, so what we say is that the code that runs on our device, which is the GPU, is parallelized by each thread running on a core. So we've got lots and lots of cores, and each core runs one specific thread, and sets of these threads are grouped together in blocks. Okay. At the moment, with the library and the state it's in, for the most part, you will find that blocks can take a maximum of 1,024 threads. Okay. When we look at this again, putting side by side the physical and logical model, what we will see in the top right there is the different streaming multiprocessors, which have the little green circles, which are each of their cores, with the L2 cache in the middle so that it is accessible, the DRAM on the right so it is accessible, but a little bit slower. And then inside of each of the streaming multiprocessors, the part that's in light blue is the shared memory, which is the level 1 cache, a register file, which has got 32,000, well, just over 32,000 32-bit registers, and the little green circles being the cores. So that is the physical layout. Then on the bottom right, we've got the logical layout, where we show that we've got a kernel, which we'll talk about in a moment. And then on the device, we have got in pink a grid, and a grid is a collection of blocks. So in that grid, we have got 16 blocks. And inside of each of those blocks, there are a number of threads. And those threads are going to be divided into what we call warps. So warps are 32 threads at a time. Okay. So in an NVIDIA GPU, the basic unit of execution is the warp. Okay. But we can have multiple warps that can be executed on one streaming multiprocessor all at once. Okay. And as we said earlier, threads from the same block will have access to a shared memory, and their execution can be synchronized. Okay. So a lot of our programming, or our thinking around our programming, is going to be around what we can synchronize and what we can allow to run, in parallel at the same time without having to wait between access to memory points. Okay. Now, I've referred to this concept of a kernel. Okay, so this is not the same as the Linux kernel. This is now what we refer to as a function. Okay, so a kernel is an extension of the C++ language that CUDA makes available for us. And when you call a kernel, you give it an execution configuration. Okay, and inside of that execution configuration, you say by how many threads you want this code to be executed. Okay, so a normal function that you write in C++ is just going to be run, with one thread in the CPU. Here, by just calling the kernel, you already have to specify how many times you're going to parallelize it. Now, in order to define a thread inside of our code, we need to use the global declaration specifier, so it's available everywhere, as well as the number of threads that need to be given to that specific kernel when it runs it. Inside of the code, each of the threads that executes is given a unique ID. So it knows which ID it has, and it also has access to its own local variables. Okay, it can see what its ID is through a number of built-in variables that are effectively passed to this kernel when it runs. So if we look at a bare bones example of this, we can look at just this, the kernel function that we will see in the example a little bit later, which is just around vector addition. Okay, so what you'll see is in the main function, which is obviously where the CPU is going to run from, the kernel is invoked with three, larger than and smaller than symbols, the little, arrows. And it is indicated as having a 1 and an N. Okay, so that means that our grid has got only one block inside of it, and N is the number of threads that are inside of that block, and it passes in pointers to three arrays, which are of type float. And then what you will see is inside of the kernel, okay, the first thing that is collected is the variable I, which is just the thread identity. Okay, so each time this function is run by a specific core, it's going to look at what its own thread ID is. Okay, and then it uses that index variable to look inside of the array and only perform the operation on one position inside of that array. So in other words, thread number 5 will look at the 5th index inside of the array for A and B, take those values and add them together and put that into the 5th index of array C. And the same is going to be true of index 1, 2, 3, 4, 5, etc. Okay, so that is how we parallelize things. Okay, so we invoke it using our execution instructions, and it pretty much handles all of the rest for us. So as we learned now, threads run on a core, so each thread is going to be run on its own core. blocks are run inside of streaming multiprocessors. Okay, so we obviously want to contain that within a streaming multiprocessor. But we can also specify very large grids that can effectively take up the entirety of the capacity of the GPU. So we can run a huge amount of threads just depending on how we set up the layout of our kernel grid and our blocks. Okay, so in order to know which thread I am as I'm running in parallel, there are a number of variables that are passed into each of those kernel functions when they are run, which allow each thread to identify themselves. So the first one is the thread thread ID. Okay, so that is the thread index. So that is within the block that I am in. Which thread am I? Then next, we've got the block index. So in which block do I find myself? And then at the same time, we've got the size and shape of each of the blocks, as well as the size and shape of the grid that we are going to run this in. Now, in this lesson, we are going to concentrate on threads that are run in a one-dimensional block, but because we are also working with processors or GPUs that have been set up for graphical work, we find that we can also very easily define blocks that have 2 dimensions or even 3 dimensions. So depending on the nature of the parallelization strategy that you want to use for your problem, defining the block differently may actually be quite useful to you, okay? But in this instance, let us focus on one-dimensional threads. Now, when we do the execution configuration, there are 4 variables that we can pass. The first one is the dimensions of the grid, okay? So this is as a dim3, so in other words, a 3-dimensional variable that just define the size of the grid, okay? And this tells us the number of blocks that are being launched. The second variable is dB, which is also 3 dimensions, and that tells us the number of threads per block, okay? The third variable is the number of bytes of shared memory that is dynamically allocated per block for this call from the statically allocated memory. And the fourth variable is the associated stream. So this is optional, and we will talk about that a little bit later. So for now, what we're going to do is consider just the first 2, because the other 2 variables are optional when you do your execution. And we're going to consider them in one dimension. Okay, so now that we've got quite a bit of theory behind us, we want to work through an example so we can see how code is actually written for these sorts of processes. So the example that we're going to use is effectively doing 2 things. So it's a simple program that is going to allow us to collect device properties, so we can learn more about the CUDA device that we're working with. And it's going to do a bit of parallel processing in the form of vector addition. Okay. First, we're going to conceptually work through this in the form of a flowchart, where we will look at which specific parts run on the device and which specific parts run on the host. And then finally, we will go through just pseudocode, just so you can see how the things are structured in code. And then finally, we will actually go through just a little bit of a review of the actual code. And that is also the code that you will find available on the GitHub repository and the Dropbox that we will share. So if we look first at the flowchart. So what we're going to do is on the left-hand side, so we start with main. So obviously first, we're going to include all of our CUDA libraries and our standard C libraries. And we're going to start in main, because all C++ programs or C programs start with main, okay? Then the first thing we're going to do is we're going to output the device properties. So that's a function that we will call. Then we're going to get data from the host, so on the CPU side of things. Then we're going to call add, and this is going to run on the device. So that is taking the host data, and then we're going to do the vector addition. We're going to output our results, and finally, we're going to reset the device, and then we're going to exit. Okay. So if we look at that first function that we've got specified, that is output device properties. So all of the things that are running or that are sort of gray-blue, those are running on the host. Okay, but when we call output device properties as a host function, the first function it's going to call is CUDA get device properties. So that is hitting the CUDA library, and it is going to query the actual device that we are working on. So it's marked in yellow because it's hitting the device, but it's not running in parallel at that point in time. Once we've gotten all of these device properties, we're just going to print them to the console, and then we're going to end the function and return back to main. Our next function is going to be add on device. So this is where we do the vector addition. So it's the little helper function. So the first thing we're going to do is we're going to create pointers to the GPU memory on our host. Okay. Next, we're going to set our CUDA device, because obviously you can have more than one CUDA device at a time. So we obviously have one in this specific setup, but you need to specify which one you're going to use. Then we're going to allocate memory on the GPU for the data that we've passed. And we're going to then copy from the host device memory, the host memory onto the device memory using CUDA mem copy. Okay. So those things are all basically running against the GPU, but not yet in parallel. The one that is in green, however, that is the kernel. So that is, we call that add kernel. And that is where we will run our code in parallel, where we are just going to be performing the vector addition. So it runs all of its threads in parallel, it ends and returns. Then we are going to call sync on the device. So we're going to synchronize the device, let all of the threads finish running before we get to this point. Next, once everything is synchronized and we are sure that the kernel has finished running, we were going to copy again using CUDA mem copy from the device back to the host. Then we are going to free the allocated memory from CUDA and end the function, which then returns us to main. We output the results that we had, reset device, and then our program is finished. Okay. So that is roughly what we want to achieve, with this little example. So let us now look at the pseudocode of how we are going to achieve this. Okay, so first, we will look at including the header files. So the two libraries that we're going to include from the C standard library, obviously there are multiple ways to include libraries. I've included all three of them here. You can include sort of local things. You can include just the header files. You can include the libraries as a whole. C++ gives you all those options. So I just wanted to give you a bit of variety. But what we want to include specifically is the runtime. So the CUDA runtime, which allows us to hit the library. We want to get the launch parameters of the device. And then standard IO and string are just standard libraries that we will use in our C++ program. Next, I'm going to declare the two functions that we specified. So I've got add with CUDA with a lambda error. I'll explain what that is in a moment. And what this function does is it takes in three pointers to arrays A, B, and C. And then it's got a size, so however big we want those arrays to be. And then we've got the output device properties function, which is also going to be the one that we call, which just prints some of the device properties onto our console. And the next thing we are going to define is the actual kernel that we want to run in parallel in threads on the GPU. So we've called it add kernel. Again, we are going to define or pass it in the three pointers to our arrays. But as you will see here, what I'm pulling out is just the thread ID. Okay, so I just want to know which thread I am as variable I, and then it is just one line of code to say that in the output array C, I want to get the addition from the elements from the A and B arrays just added together. Okay, so that is the part that is going to run in a number of threads on the GPU. Okay, so that's just the functions that we kind of define at the top. Now, if we look a little bit deeper into the output device properties function, this looks like normal code. The only thing that we're going to be calling from the CUDA toolkit library is going to be CUDA get device properties, version 2. Obviously, we're on a slightly newer card, so we can get the version 2 functions. And what this is going to do is we pass in the prop variable, which is just a structure called CUDA device properties. So we pass that in as a reference. And we're looking at device 0. In this instance, we've only got one device, so it is indexed as device 0. And then I'm just going to, from those properties that I read, I'm going to pull out the global memory size, the size of the L2 cache, the clock rate that the GPU is running on, the number of streaming multiprocessors that are on this GPU, the number of blocks that can be run on each streaming multiprocessor, the number of threads, the maximum number of threads that can be run per block, and then the warp size for this specific processor. Now, because this is a pseudocode, you will see that I've put a comment there in the between the print statement and the CUDA get device properties that just says exit on error reported. Once we look at the real code, I will show you how we do our exiting strategy in case there are errors, because obviously error checking is quite important in all code, but specifically when your code is running on a separate device to your CPU in parallel, doing its little job. So you want to be tracking your errors very, very carefully. So that is our output device properties function. The next function is our helper function for doing the addition. So the first thing I'm going to define here is I'm going to give it a lambda function, which is just going to basically clean up all of the memory that I've defined, write out the error string to standard error if there are any errors, and then return an error code if there is an error code to return. Well, obviously, there will be an error code to return. Obviously, something like CUDA success, comes back as an error code. It's not an error code. It's actually just a state. So this is just a little lambda function that I've written so that it can be internal to this function. The other technique, so if you look at some of the example code you will get from Microsoft, they use goto statements. I just don't like goto statements, so I find lambda better, but both will work. Okay. So next, once we've got our little exit lambda function defined, we're going to declare our status variable. So this is going to keep track of the status of things every time we run a CUDA function. We next want to create pointers from the pointers that, or the pointers that are passed into this function are currently sitting on the host side. Now we declare 3 variables that are going to sit on the device side. Okay, so that's on the GPU side. Next, so this is obviously quite a bit of code, but it's all the steps that we highlighted inside of our flowchart. So the first function we run is CUDA set device. So we're picking the first device because we only got one, and then you will see it says exit if there's an error message, and the error message we are going to throw is that CUDA set device failed, and we're going to ask, do you have a CUDA capable GPU installed? Okay. The next step we're going to do is we're going to allocate the GPU memory to the pointers that we've created. So that is where we call CUDA malloc. We pass a void pointer from the reference so that we can dereference it. And the size that we're going to allocate in the memory is going to be the size that we passed in. Okay. And we do this for all 3 variables. And every single time, if we have any kind of error, we throw the error message, CUDA malloc failed to our standard error. Okay. So once we've allocated the memory on the GPU, we're going to copy the data from the host to the device. So here we are obviously, the first thing we're going to copy is just the 2 input variables, so A and B. We are going to pass in the dev A, which is the pointer to the GPU memory. We're going to pass in A, which is the pointer to the memory on the host. We're going to give it the size, and obviously the size of the int data type. And we're going to call CUDA memcopy host to device as the direction. Okay, so we've copied from our host to our device. Then we're going to call our kernel. So this is actually where we say run this in parallel. we are saying that there is only going to be one block in our grid, and that block is going to run size number of threads. So if they are, if the size of each of the arrays is 5, then we're going to run 5 threads, and we're going to pass in the 3 pointers to the memory that is on the device. We're going to then check for errors. So we're going to call CUDA get lost error. If there are any errors, we throw out what the specific error was that was reported. Next, we are going to synchronize. So we're going to wait for the kernel to finish running before we do anything weird. And we're going to return any errors that we find in the synchronization. If there is an error, then we will obviously report that interstate error. And finally, we are going to copy. We're going to call again CUDA mem copies, the same function, just obviously with the variables reversed. So this time, the destination is going to be C, which is on the host. The source is going to be dev C, which is on our GPU. The size is the size that was passed in, and the direction is CUDA mem copy device to host. And then we will finally return the exit with status, which is our little lambda function. So in each of those comments where I said, we would call the exit, that is calling the lambda function. We pass in the 3 variables, which are the pointers to the locations in memory on the device, so that we can clear that memory, and we pass in the specific status. Finally, if we look at how we will call this from main, so this is obviously everything running on the host, we again get an error, CUDA error variables, which just tracks our status. We call the function output device properties, and we return if there is any kind of CUDA error. If there is a CUDA error, then we will exit with a return of 1 to show that our program has failed. Next, we set up the data that we want to use on the GPU for parallel calculation. So what I've got here is now an array of size 5. So I want to have 5 threads. In my A array, I'm going to have the values 1, 2, 3, 4, 5. In my B array, I'm going to have the values 10, 20, 30, 40, 50. And then the C array, I just currently initialize to have a value of 0, because that's where my answer is going to go. I'm then going to call my add with CUDA lambda error function, the helper function. C is my output variable. A and B are my input variables, and array size, we specify it as 5. If there are any errors reported, we will obviously pull them out here and return with an error state of 1. If, however, there aren't any errors reported, then I'm going to just print to the console what the end result was by printing out the 5 variable or the 5 indexes of my C variable. I'm then going to reset my CUDA device, and if everything worked well, I will return with a value of 0, indicating that my program was successful. Okay, so that is roughly what we're going to do with our example code. So if I was to run this, what I will see is the output on the bottom. So first I get the information about my device. So it tells me that the global memory size is just over 8 gigs in size. My L2 cache is 4 megs in size. My clock rate is 1.77 gigahertz. The number of streaming multiprocessors on the specific card is 48. The number of blocks I can have per streaming multiprocessor is 16. The number of threads that I can handle per block is 1024, and the standard warp size is 32. And then, as you will find, if I add the 2 arrays together, it gives us the answer that we expect of 11, 22, 33, 44, 55, because it's added everything in by index. Okay. So that is basically our first, proper CUDA program running things in parallel. Obviously, in the next lesson, we will talk a little bit more about how we can make this more complex, how we can use the multiple dimensions and add things in matrices and such. But for now, if you can get this running, that means you can run code in parallel on your GPU. Now, to get yourself up and running with this sort of a setup on a Windows environment, it's quite easy. You go to developer.nvidia.com and go to CUDA downloads. That will give you access to the newest CUDA toolkit, which is version 12.4. You can download it for Linux or Windows. Obviously, in this case, I will be downloading it for Windows. And then what is I don't know if I count it as a disadvantage or an advantage, but obviously on the Windows environment, it's pretty much built to work with Visual Studio. So you would need to download Visual Studio as well in order to get, the full experience out of your CUDA toolkit. You can use command line tools and all sorts of stuff like that. It's just that Visual Studio does do a lot of the heavy lifting for you and kind of identifying devices and drivers and getting the libraries working quite nicely. So I would recommend with going that way unless you have very strong feelings against using Visual Studio. So now, depending on how much time we have, what is my time?
You have 15 minutes.
15 minutes. Okay, perfect. Then we have enough time to just go through the code a little bit in a little bit more detail. Okay, can you see my code, Martin?
It's a little difficult to see if you could zoom in. I don't know if that's possible.
I think I can. Okay, that is what is that better? I hope so. Okay, so as we indicated, this is where we add our libraries. So those are the ones you're going to generally be using, well, at least these ones. But there are a large variety of libraries that you can use from CUDA for different operations, depending on what you want to do. This is obviously just running with the base runtime library. Then we define our two functions, our two helper functions, the add with CUDA, as well as the output device properties. Then we define our kernel, as we showed. So as we said, this one is going to take in the 3 references to memory, and it is going to hit them in parallel, one by one, looking at the thread ID to see how far into the index of the array to run each of the individual thread operations. Then we have our main. So we described what the output device properties does when we were looking through the code. What we're going to just do here is this is how we capture our errors. Okay, so we output from each of the functions we run against the CUDA library. We output the CUDA status, which gives us that error type. If the error answer is CUDA success, then obviously there was no problem. If the status is anything other than success, we obviously say that there was some problem, and then we write some sort of error message to our standard error so that we can debug it a bit later. So in this instance, if there was a problem in getting the device properties, we call the error that we failed reading device properties, and because it's C++, we return a value of 1, indicating that the program has failed. Next, I'm going to define the data. As we said, it is 3 arrays of size 5. With the values of 1, 2, 3, 4, 5 in A, and 10, 20, 30, 40, 50 in B. And then the C array just initialized to 0 because we will fill it up by pointer later. Then we call our add CUDA lambda error function. We again are going to just check for the status. If there was an error, we will indicate that that function has failed, and we will return a value of 1. If it didn't fail, then obviously we will output the results of the operation to the console so we can see our answer. We will reset the device. If the reset fails for whatever reason, we will obviously say that the CUDA device reset has failed, return 1. If everything has worked appropriately, we return 0, indicating that the program has run successfully. If we look at the function specifically, again, the only thing that's different here from the pseudocode is just looking at the error. So here, I misnamed this. That shouldn't be add with CUDA. That should be output device properties. But output device properties has failed if we have anything other than success. If we did have success, however, we will print out the properties that we read from our CUDA device onto the normal console, and then we will return the status, which will at this point obviously be CUDA success. Now, for the add with CUDA lambda error, so this one is a little bit more complex. Here is the lambda function I was talking about. So in languages like Python and C++, and C# and Java, you can define internal functions inside of classes and other functions. In C++, you actually can't. So the only way to get around doing an internal function inside of C++ is to use an anonymous function, which is what we would call a lambda function. So to define a lambda function, you give it square braces to say it doesn't have a name, and then you pass in the parameters that you want it to use, and then it is defined or written exactly the same as what you would do a normal function. It returns the error state, but you just assign that to a variable of type auto because it should know what kind of a function it is, and then you can call it like any other kind of function. Okay, so that's just a workaround to get internal functions in C++. So the three things we want to do is the three variables that we defined on our device memory. We want to free them, so we're going to free C, A, and B. And if there was any kind of error that we pass in, so if there's a string in the error message string, then we're going to print that out to standard error, passing in that string, and then we're going to return the error state, which is the CUDA state we get from the device. Next, we define the pointers to our three variables, obviously on the device now, and we again define a error status or CUDA status variable. Then we set our device, we pick device 0 because we only got one, and then I'm going to call my lambda function if I have any kind of error. So if I have an error, I'm going to exit with status. I'm going to pass in the three variables to clear the memory, passing the status code that I've got, and some sort of informative message to say that if it failed at this point, this is why. So in this case, CUDA set device failed. Do you have a suitable GPU device? Next, I'm going to call CUDA malloc, which is just going to allocate memory on my GPU for each of the variables. So C is the output variable, A and B is the input variables, and they are all going to be of size that I pass in. And if any of them fail, again, we are going to clear that memory, clear that memory, clear that memory, and we're going to say CUDA malloc has failed, just so we know where it failed. Then we're going to call memcopy to just copy the two input variables from our host memory to our device memory, indicating the direction as CUDA memcopy host to device, going from our CPU to our GPU. If it fails, we run our lambda function. Then we call our kernel. We have indicated now our execution parameters are that we have one block in our grid, and that block has size, number of threads, so 5 threads, and then we pass in the pointers to the memory that is on the device. The kernel does its bit, and then we check if there are any errors that were given. So it looks at the last error that was given by the device. If there is anything other than success, we obviously report that and say that the kernel has failed to launch and failed to run successfully. Next, we are going to synchronize the device to make sure that all of the threads have finished running before we continue on with our sequential code. If we have any problem with synchronization, we are going to say that the synchronization has failed, again, clearing everything with our lambda function. And the final step we are going to do is copy the answer from our output variable on the GPU back to our host variable so that we can access it in main again, this time indicating that we will do CUDA memcopy from the device to the host. If it fails, CUDA memcopy failed. And that is pretty much it. We will exit with status, and you can run from there. So at that point, I think we've experimented code. I've added a number of references for, where I got information and images. So obviously, thank you to the internet for having lots of great images available to me. And at this point, I want to thank you for your attention. I hope that you have gotten lots and lots of answers from Professor Martin in the Q&A. But if there are any other questions at this point, I'm happy to take them.
There's one person who has their hand up.
Okay. Graham, I think you are the one that need to look at someone with their hand up. Viduranga. I'm not sure if we can make you audible.
I'm not sure how to do that.
Yeah, I don't think I have permission to do that.
And there's a second person who, let me think, how do we do this?
Yeah. Viduranga, can you maybe put your question in the chat or the Q&A? I'm not sure if you are still with us.
There's one question with open. Can you run OpenMP with CUDA?
I'm not certain. I've never used OpenMP. I would be lying if I said.
I think MPI, which is more explicit rather than suggestions. I'm pretty sure that you can, combine those. But I think my guess would be no. But we can find that out and get the answer next time.
Yes, we can obviously make the PowerPoint available. So as we shared the PowerPoint last time on the Dropbox link, we will put it again on that Dropbox link. And there was also a suggestion to add it onto the NITheCS website, which I think we will do as well. So yes, the PowerPoint will be available.
Yeah, Francesco wrote to Belinda asking her to post that, and then we can put things in the Dropbox. So it would be good to look at that link and maybe also throughout the week.
Perfect.
Okay, can we use the PowerPoint? We'll post that.
Yes. Okay, then there's a question. I would like to ask about the allocation or copying data from the host to the device. So in the case of your data range to about 1,000 in size and have more than 3 parameters, do you have to do the copy line by line for each argument? Well, no. So obviously that's where the memcopy functions come into play. There are lots of functions available for you to do blocks of memory across. So, I mean, I guess from a thread perspective on the CPU, yes, it would run the copy effectively line by line, just because CPUs are going to do that, an instruction at a time. But once it is on the device, you can run it in parallel, very quickly. So that is obviously where one of the bottlenecks is always going to be, is when you are transferring memory from your host to your device, that can only run at a certain speed. And as I pointed out, and we will go into a little bit more detail in the next lesson, but the way you interact with memory on the GPU is also obviously going to impact the speed that you can run things in. So optimizing for memory is very important. Would I be correct in assuming that there are straightforward ways to copy customized data structures from a hosted device? Yes. So obviously, you need to program in a clever way, and that's where experience comes in. But one of the benefits with C++ is, I mean, everything is effectively a structure. So even if you're doing very complex kinds of code, you can structure it correctly on your C++ side, and then just cast it. Or use something like a union to cast it into an array. So you can do block copies very, very easily if you play around with structures, unions, and memory pointers. So yes, there are absolutely ways that you can do that in as optimal a way as possible.
I mean, if I may,
yes,
think,
please,
I mean, the memcopy is very generic. So, things are laid out in a one-dimensional way.
Yes.
And the argument is just the number of bytes to be copied. So it doesn't care whether it's, an array of structures of the same size or the format of the data. I think the thing that you cannot really do within the device is sort of malloc, where we use dynamical memory allocation, and we can make these very complicated pointers to pointers and stuff like that. So that has to be done a little differently in CUDA as far as I know. So that's one sort of freedom that makes it a little harder to program.
Yeah, no, that makes I would absolutely agree. Okay, Graham, are you with us? If not, then I think I'm going to thank everyone. And Prof. Martin, thank you for answering the questions on the Q&A as well as in the chat. It's always very useful to have two people presenting. And thank you everyone who attended. We hope that you found this interesting and that you will join us again for the next session next week. Have a great afternoon further. Cheers, everyone.